In this video, I continue a discussion of simple harmonic motion. On this slide, I show a relationship between simple harmonic motion and circular motion. In Figure A, we see a shadow movie of a ball made by projecting a light past the ball and onto a screen. As the ball moves in uniform circular motion, the shadow moves with simple harmonic motion. Below, in Figure B, we see a block on the spring, which also moves with the same simple harmonic motion. The phase constant. What if an object in simple harmonic motion is not initially at rest at x equal a when t is equal to 0? Then we may still use the cosine function, but with our phase constant measured in radians. In this case, the two primary kinematic equations of simple harmonic motion are now position is equal to a cosine of omega t plus the initial phase angle, or phase constant, and the velocity is equal to the derivative of the position minus omega a times the sine of omega t plus the phase constant, which is equal to minus the maximum velocity times the sine of that same argument. Note in the figure that the x component of the particle's position describes the position of the ball's shadow, as shown in the previous slide. On this slide, we show examples of oscillations described by different values of the phase constant. In the column to the left, the phase constant is equal to pi over 3. The object is moving to the left, and the initial condition for this case is that x is equal to 1/2 a. When this is the case, the phase constant is pi over 3, and when we draw the plot of position versus time with this initial condition, we see this figure, and when we plot the velocity for the phase constant equal to pi over 3, we get this figure. We can also have the same initial condition of x equal to 1/2 a, but have the situation where the object is moving to the right instead of to the left at t equals 0. And if that's the case, the phase constant is now minus pi over 3. And this time, when we plot the position with this initial condition, the position versus time curve looks like this plot, and the velocity has been shifted due to a different initial condition. And lastly, we consider the case where the phase constant is pi radians, and in this particular example, the initial condition has the position equal to minus A. And when we plot the position, we get this function. And when we plot the velocity, we get this function. In this example, we will study using the initial conditions. An object on a spring oscillates with a period of 0.80 seconds and an amplitude of 10 centimeters. At t equals 0 seconds, it is 5 centimeters to the left of equilibrium and moving to the left. What are its position and direction of motion at a later time, t equal 2 seconds? We'll model this motion with an object oscillating on the spring, and it's in simple harmonic motion. We can use the figures that were on the previous slide to get an idea of what's going on. They tell us at t equals 0, it's moving to the left of equilibrium. So it would be like this first situation, except it's on the other side of the equilibrium point, so it's somewhere up here. We can find the phase constant from the initial condition. At t equals 0, the initial position is minus 5.0 centimeters, and that's equal to A times the cosine of the phase constant. This condition allows us to solve for the phase constant equal to the inverse cosine of x0 divided by the amplitude, or inverse cosine of minus 1/2, which is plus or minus 2/3 pi radians, or plus or minus 120 degrees. And because the oscillator is moving to the left at t equals 0, it is in the upper half of the circular motion diagram and must have a phase constant between 0 and pi. Thus the phase constant is 2/3 pi radians. This corresponds to an angular frequency of 2 pi over the period, or 2 pi over 0.80 seconds, which is 7.85 radians per second. Thus, the object's position at time t equal 2.0 seconds is equal to A times the cosine of omega t plus the phase constant. A is 10 centimeters, and omega is 7.85 radians per second times the time 2.0 seconds, plus the phase constant we just solved for, 2/3 pi. And that calculates to 5.0 centimeters. The object is now 5.0 centimeters to the right of the equilibrium. But which way is it moving? There are two ways to find out. The direct way is to calculate the velocity at 2.0 seconds. When we do that, we find that the velocity is plus 68 centimeters per second. The velocity is positive, so the motion is to the right. Alternatively, we could note that the phase at t equal 2.0 seconds is 17.8 radians, and divided by pi, you see that that phase corresponds to 7.67 pi radians, or 4 pi plus 1.67 pi radians. 4 pi represents 2 complete revolutions. The extra phase of 1.67 pi radians falls between pi and 2 pi radians, So the particle is in circular motion, and the particle in the circular motion diagram is in the lower half of the circle and moving to the right. In this quick check, we have a position graph of a mass oscillating on a horizontal spring. What is the phase constant? The correct answer is A, minus pi over 2 radians, which we can determine by using the circle diagram shown to the right and below. Here where it's shown that the position initially at t equals 0 is 0 and the velocity is positive. Here is another example where the initial position is shown to be minus a at t equals 0. What is the phase constant in this case? Well, let's look at the circle shown in the bottom figure to the right. It's shown there that x is equal to minus a, and the velocity, initial velocity, is 0. So the correct answer is pi radians. We know that the initial velocity is 0 because we draw the velocity as the tangent to the position curve, which in this example, at t equals 0, is horizontal. So it corresponds to a 0 slope or 0 velocity. In this quick check, the figure shows 4 oscillators at t equals 0. For which of these is the phase constant equal to minus pi over 4? So once again, we draw the situation on the circle. And we see, in order to have a phase constant of minus pi over 4, that it must be moving to the right and be beyond the equilibrium point. So the correct answer is C. And that concludes this video.